Hi, my name is Dennis Derrickson. I'm a professor at California Polytechnic State University and part of the electrical engineering department. So I've been doing a series of videos on noise, and this time I'm going to talk about power supply noise. So many of the little circuits I built here are hooked up to a power supply, and I've been ignoring any contribution on the power supply and what it could do to add noise to a circuit. And this time I'm going to look at how big of an issue that might be, power supply noise. So let's look at a typical power supply circuit. You have an instrument which is going to provide a constant voltage, and then you'll have a load, and you'll provide current through the power supply through the load. In a perfect power supply, what we'd like is that this power supply is capable of measuring any current. So an ideal power supply can do that in this symbol right here. The second thing we want to do is make sure that the AC impedance of this supply is zero ohms, so that the voltage can never change across it. That's important for noise also. And the second is that we want this noise, this voltage right here to be absolutely rock solid, have no noise on that at all. And is that true? So, well, in any kind of power supply, although it looks like a simple symbol, there are transistors and diodes and integrated circuits, and they all have noise, including thermal noise, shot noise, 1/f noise. And it's possible that all that electronic circuitry in the supply can actually produce its own broadband noise. Also, the power supply is hooked to the wall outlet, and 60 hertz signals can come in, or it can be generated with an oscillator, like a switching power supply, and those oscillator frequencies can show up at the load. So we'll try to look at various different power supplies and see what kind of noise they might have. Okay, so we did several experiments, and the first experiment was we choose 6 power supplies. These 3 power supplies are switching regulator power supplies, mostly quite current and on the market. And then I had some linear power supplies, linear regulator from quite a few years back, middle range. And then we have this measurement instrument, which has a power supply, but it also has the ability to measure baseband noise. And we'll use this Keysight SSA-X 5058A to be both a source of voltage, but also the measurement tool that will allow us to compare the noise contribution of all these 6 different power supply examples. So let's look at the first experiment. We are going to have 6 power supplies, and all the power supplies are set to 3.3 volts, the common voltage for various integrated circuits. All power supplies are going to have no DC load, and we'll measure the baseband noise between 1 hertz and 10 megahertz using the Keysight SSA-X baseband correlation receiver, which is shown here, and I'll show you a little bit how that can measure such small signals in a second. The second experiment is I'm going to take some of these power supplies that may have more noise than we'd want, and I'm going to put it through a low dropout regulator that has low noise and high bandwidth, and I can show you how we can essentially, from any of these power supplies, suppress the noise with this external low dropout regulator. The third experiment, which I won't do today, is to hook these power supplies to various different power devices under test, probably amplifiers, and see what implications of having noise on the power supply will do to the performance of the amplifier or other components, especially in an analog system. Okay, so let's set up this experiment here again. So we're going to take power supplies, 6 different power supplies, and we're going to apply it to this Keysight SSA-X, which has a really sensitive correlation-based receiver, and it covers 10 millihertz to 10 megahertz offset right here. So we're going to have displays where we have log frequency here, and we're going to display the noise level in dB compared to a volt. This shows here the architecture of the correlation receiver behind the front panel on this baseband input. So on the input, we're going to see that it is terminated in a 50 ohm resistor. and that's AC coupled to two different channels. It's analog to digital converted, and then FFTs to get the frequency domain view of these two channels. And then we're going to do something called a cross correlation. And the cross correlation will allow us to cancel out all the noise in channel 1 and channel 2 with some mathematical operations. So just a quickie on what this cross correlation does to give you very sensitive noise measurements on the power supply. If you bring up this baseband noise personality, you'll find out we have the device under test, which is the power supply. We're going to AC couple into an amplifier that has variable gain with a 50 ohm input impedance, and there are going to be two amplifiers in parallel. And then we're going to do cross correlations to get really good noise measurements. And we can also change the gain of these amplifiers from 0 to 50 dB depending on our application. Okay, here's an illustration that hopefully tells you what this correlation receiver is doing and why it can allow you to measure noise at such low levels. So here we have the input noise right here from the power supply, and I'm going to arbitrarily assign a noise element in the power supply at some frequency that has some magnitude here of 1 unit and some phase of 45 degrees. So that's the power supply example input noise right here in a complex noise representation. Then we'll have a amplifier chain, two identical amplifiers right here. Channel 1 gain will have noise of its own. Channel 2 gain will have noise of its own, but the noise magnitude and phase and the magnitude of phase of this noise right here will always be uncorrelated. They have no relationship to each other. But the noise from the power supply will go through both chains right here, and they will be amplified from the power supply noise, and they will be correlated. The power supply noise will be correlated between these two receivers. Here I show a channel 1 noise as 0.5 amplitude, angle of 125. Channel 2 noise is 0.5 angle of -80 at a particular time and frequency. They're always moving around. After we digitize it in the analog to digital converter and fast Fourier transform into the frequency domain, we'll have channel 1 output being the input noise right here amplified plus the channel noise amplified at different frequencies. And then channel 2 after FFT will have channel 2 noise plus the same input noise amplified. So these are the signals we're going to have. So here I show vectorially adding the input noise signal plus the channel 1 noise vector to get the resultant vector. Here we have input noise from the power supply plus the channel noise giving you this resultant vector. And in the frequency domain, we're going to do this cross correlation operation. We're going to take the channel 1 frequency information, and we're going to do a channel 2 conjugate. We're going to flip the phase of the complex of the signal. We're going to multiply them together, and here's an example of the resultant channel 1 plus input noise here. This is resultant channel 2 plus input noise. And it's conjugated right here, because this was the noise right here. We conjugated it by flipping the phase. We multiply them together, and we get this vector right here, which is 1.08 angle of 60, which is not the same as the input, but it's close, and the angle is close. And after many correlations, doing this over and over again, we can eventually converge on the input noise amplitude and phase, and we will negate and cancel out all the channel 1 and channel 2 noise. So that's why we get this great sensitivity on this cross correlation receiver architecture. Okay, let's look at some of these power supplies. So inside the Keysight SSA-X, we have a couple power supplies that are internal to this instrument. So we take those power supplies and put it to the correlation receiver input. This is the measurement we get. So we did these numbers right here are the correlation numbers at different offset frequencies. And at the lowest frequency offset, we have 50 correlations right here. And so this orange area represents kind of the floor of the measurement. You have to do more correlations to reduce that floor. But the output of this power supply right here is pretty good, almost featureless. We can see a little residual 60 hertz spur and a little residual 120 hertz spur, but very good noise performance over the whole frequency. But We don't know how much lower it is because we're kind of running on the floor of our correlations right now. So let's, instead of do 50 correlations, let's do 500 correlations. So we're going to do 10 times more correlations. And now our noise floor of the measurement system drops, and we get a little bit better indication of where the noise is actually at. And we see a little bit of noise that's real from this power supply, and it's coming above the noise floor here. At 10 hertz, as an example, we went from minus 132 dB volts floor to a minus 135 dB volts floor right at 10 hertz. So we got an improvement by taking more time. We go to the extreme where we do an overnight measurement, and we now are doing 2,500 correlations at the lowest frequencies. And now we get a noise floor of minus 140 dB volts. And so it looks like the noise is actually smaller than that. We'd have to do more correlations to figure out where the actual floor of the noise is. But pretty good performance from this instrument. And that makes sense because this instrument was optimized for low noise, both on the power supply and on the measurement of noise. Let's look at the other power supplies now. So we looked at a Keysight N6705C, which is like a system power supply. It's 4 different power supplies. It's a switching power supply. And we look at we compare the noise of the SSA-X right here power supply to the N6705C. And you can see there's clearly measurable large noise right here. A little bit of 60 hertz, not too much, but we have a lot of discrete stuff out here, probably with a switching power supply. So substantially higher noise in this power supply over a broad frequency range. Okay, let's look at a different one. We looked at, this is another switching power supply, a Keysight E36103B. Its shape of its noise is a little different, but it does have different switching frequencies, different discrete components. These discrete components we're going to call spurs, as opposed to this broadband, which we're going to call noise. These signals don't scale with the correlation since they're a signal-like environment. But you can see there's significant excess noise above the noise produced in this SSA-X in this small single power supply that you can obtain. Here we have another system power supply. This one's a little bit earlier in time. It was from Agilent, a predecessor company to Keysight. And it has broadband noise, a lot of spurious signals right here in the switching area, and some discrete 16 to 120 hertz signals, but different signature, but clearly measurable broadband noise output versus frequency on this switching power supply. Now we'll go to a really old timer here. This was a HP 6216A, which is a small single power supply produced in the 1970s, maybe a little bit later. And overall, its broadband noise is much lower, but we do have a lot of 60 hertz related spurs right here, but not bad for a power supply. And this is a linear regulator power supply. Then we go to another 6236 HP, an older power supply, a triple output power supply, and it has lower broadband noise, but it has plenty of spurs right here and 60 and 120 hertz noise too. But the noise out here is significantly lower than some of the other power supplies, but still measurable. And I just here, just to see them on top of each other, I went into Excel and plotted the SSA-X, kind of the lowest noise of the sources we had, some of the highest noise switching power supplies, and some intermediate ones right here, which were linear power supplies right here. It's like this blue one that is much better, but still has significant spurs right here and noise shaping right here, which is not at the level of the instrument that's been optimized for power supply noise, which is the SSA-X. So what's the conclusion from these experiments? Well, I didn't try to go into the design of all these power supplies, but I just wanted to show that you can pick a power supply off the shelf and there can be various levels of noise, both in the spurs and in the broadband noise. And in many instances, especially of sensitive analog circuitry, that broadband noise from the power supply can get put on the sensitive analog circuitry, and we need to figure out methods by which we could reduce that to get higher performance analog circuitry. So here's a picture of both a switching regulator power supply and a linear regulator power supply, saying, how can we get together and reduce our output noise? And so let's look at one method, maybe how you might do that. So we're going to move on to experiment 2. Here we use this analog regulator right here that has 2 inputs. It has input from a power supply and an input to your sensitive analog electronics. And it's a regulator that is called a low dropout regulator, meaning that the voltage difference between these two does not need to be too great, so you're not wasting a lot of power. Applications, when you look at it, they talk about phase lock loops, VCOs, mixers, LNAs, power amplifiers, all the things that you want to have for good low noise analog electronics. And they highlight the low noise right here, and you can use it as a post regulator for switching power supplies. And that's what we're going to do. We're going to take a switching power supply, put that in here, and we're going to take the regulated output right here and see what we can do to reduce the spurs and the broadband noise of a switching power supply. Okay, here's the experiment. So we took the Keysight N6705C, which has a switching power supply, had significant broadband noise. Put it into the input here before the regulator, and then we took the output of the regulator into the baseband input of the cross-correlation receiver on the SSA-X. And let's see what we got out of that experiment. So just to kind of reiterate, this was a measurement of the baseband noise that's coming from the 6507C switching system power supply when we have 6 volts on it at the output. We put that into the regulator and got 3.3 volts at the output. And here is the noise level after the switching power supply regulator, the LDO, excuse me, the linear regulator, the LDO, with a 3.3 volts output. And you can see that it does a fantastic job of suppressing the noise. There is some residual noise that shows up right here. You can see this little ledge right here. And so there's a little bit left over of that ledge right here. But more or less, for both the spurs and for the broadband noise, it really, really killed off both of those signals, spurs and broadband noise. So this is actually a very, very good low noise output right here. So you could probably power your sensitive analog circuitry after going through this regulator. So the conclusion is there are ways that you can take a power supply and reduce its noise. And this is an example of a LDO regulator to improve power supply noise. And what we're going to do next in future presentations, we're going to take these power supplies and put them on sensitive analog circuitry and see what the implications are for performance if we don't have a low enough power supply noise right here in the driving system power supply. So that's it for today. Hopefully you got some indication that don't just pick any old power supply up if you were working with analog circuitry that's sensitive, and think about power supply noise and what you might need to do to suppress it. Thanks.